Okay, so convolutional layers, right? The idea behind a convolutional layer is that we define a small patch of weights, all right? Like a little 3 by 3 patch. We then slide that patch over the input image, and the output we get is a feature map. And I'll make that more concrete in a minute, right? But we have this little patch of weights, and instead of learning, so like a fully connected thing that connects all of the pixels in a layer to an individual output neuron, we have this little patch, right? And this little patch is going to connect a specific region of the image, right? So this little patch is going to connect a specific region of the input image to one unit in the output, right? And then we're going to slide that along the image. So there will be another patch that overlaps, notice, that is connected by the same pattern of weights, right? So it's the same weights, the same pattern of weights, but it's connecting a different region of the input to a different output unit. See how that works? So we're looking for, in every region, right, the same pattern defined by this filter, but we're mapping that pattern, so we're applying that pattern to a different region and then mapping it to a different output unit, okay? And we can kind of think of that as sliding that one filter, that one little patch of weights, across the image and letting the output go to a unique neuron each time, which builds up a feature map, right? So notice that this kind of lines up with the whole receptive field thing, right? Because each neuron is getting input from a little teeny patch, right? And this lines up with the convolution. Sorry, because each neuron is getting input from only a subset of the input image, right? And this lines up with the convolution filter idea, right? Where the convolution is represented by the pattern in that patch of weights, right? This little patch of weights is defining a convolution filter or kernel, right? We can define more than one patch. Each patch represents its own feature and produces its own feature plane, right? So you get one whole set of neurons, basically, for each feature you define. If you define 12 filters, 12 features, you'll get 12 equally sized sets of output neurons, right? Where each neuron represents the result of applying one of your filters to one little region of the input plane. And if you were completely overwhelmed by this, it can be really daunting the first couple of times because you're having to think in the abstract and maybe juggle like figures around. So, the internet has we already know that. It's going backwards. There we go. The internet has a bunch of good pictures about this. This picture I got from the website Towards Data Science, which is just a Medium blog, and it is copyright to one Irhum Shafkat. I hope I didn't butcher his name. But here, right, you have a very good animation where you can watch. So this shaded region, right, that shaded region would be, so like it'd be the same weights every time, right? It might have some specific pattern. And that shaded region represents your repeating patterns of weights. I didn't do the alphabet wrong, good. As it slides across the image and builds up this, which is the feature plane, right? Or feature map. I might use feature map and feature plane interchangeably just because I'm dumb, right? I'm not sure where I got the term feature plane from. That's the one that I keep wanting to call these. Anyway, so I'm sorry for being confusing about that. Right, so here we have our convolution filter sliding across our input image and producing our feature map, right? Oops. And again, notice because of the way that it's sliding that our feature map is slightly smaller than the input image. And don't be confused, right? It's just a coincidence that the feature map here is 3 by 3 and the convolution filter is itself 3 by 3, right? It's a coincidence that this output and this shaded patch are the same size. If this image were wider, then this shaded patch would be the same size, but this feature map would be wider. So another image yoinked from the same place is this one, and so the other one might be more easier to grasp just like intuitively and visually. I actually kind of like this one better because it shows you the weights in the filter map moving around, right? So that little sub-0, sub-1, sub-2, those are the weights of the filter map. So you can kind of see how it's being applied across an image or across a plane of digits, right? And this is normal forward pass math, right? This is normal forward pass math, where each point in the input is multiplied by the corresponding weight, and then they're all summed, right? So if you want to pause this and go through and do the math here, you'll see that it's multiplying the value in a square by the weight for the square, right? And by the weight for the square and then summing them. And the thing that tripped me a little bit is trying to figure out how to say it's moving, right? So the weight in the square depends on where the filter is, right? So you see that the output is different based on where the filter goes. Yeah, anyway, I like this one because you can see the actual weight pattern moving around. So here's a very common picture that you'll often see for these things. There's a very similar picture to this that was used in the original Linnet paper, right? The LeCun paper. I don't know how to correctly pronounce his name, right? But the Linnet paper from before. There's an image that looks a lot like this. The huge advantage that this one has is that this image is CC attribute, so Creative Commons attribution share alike. Thank you very much, user Apex34 from Wikipedia. But here, you can kind of see how we get an image, and then a little teeny tiny patch gets mapped to an output unit in a feature plane or feature map. And then here we repeat it, right? So let's not worry about subsampling for the time being, but then it gets repeated, right? The next layer also performs convolutions on the earlier feature maps, and then eventually you flatten it until you feed into a normal, fully connected layer, right? So this is kind of a description of, maybe I should have put this slide later now I think of it, but this is kind of a description of where we're going with this, right? You see these pictures a lot, some variant of these. They may help you assemble sort of the concept of what's going on if you already mostly understand it. I don't think they help you figure it out if you're confused. I think this and this are probably the pictures to really study for a while if you're not sure what we're talking about right here. Oops. Right. So this simple picture really kind of only makes sense in the single channel case, because notice that one filter is being applied to one input channel to make one output channel. What if there are multiple channels, right? What if you have like an RGB image? Basically, then the words filter and kernel stop meaning the same thing. One filter consists of multiple kernels. Each kernel belongs to a channel, okay? So like red will have a kernel, blue will have a kernel, if your channels are red, green, and blue, and then green will have a kernel. Good Lord. Horrible writing, and those are out of order. Anyway, right? And then they will be combined, added, I believe, normally, to produce one filter map, okay? So your one filter map in the output will have like a red kernel connecting it to the red input, and a blue kernel connecting it to the blue input, and a green kernel that's getting slid over the green input, and then they're all summed. Okay? And that's how that works in the multi-channel case. I just tapped the volume knob for the mic. I hope I'm not now deafening you. Or muted, either or. All right, so another final little benefit of this, I've said several times that the behaviors our networks learn are maybe not necessarily interpretable. One useful thing about convolutional networks is that those little weight patches usually are fairly interpretable. We would expect those to look like a useful feature in the image, right? So if you're learning facial recognition, we would not be surprised if one of the filters looked kind of like an eye, right? Ooh, good lordy lord. Or a mouth, that's totally what that is, not like secret squirrel in a top hat, right? Or a nose, right? We wouldn't be surprised if the network learned convolution filters that look like this when it's looking for faces, okay? So convo filters can be fairly interpretable, and if you're particularly good at DSP, digital signal processing, and you kind of understand how these things normally work, you might be able to make inferences about what it's looking for and why it behaves a certain way if you examine the filters that it learns. All right, this is probably a good time for an image break.